section 13.1. This is also an area known as optimization, mainly in that we're interested in minimizing costs, optimizing profit, and a lot of times we can do this by finding the minimum or maximum of a function. So let's get into it and see how we do this with calculus. So using calculus, and this is an important application in calculus, or something you probably spent a good deal of time on in Calculus 1, is the problem of finding a local minimum of a function. Problems of maximization pretty much are covered by this theory because you simply find the minimum of the negative version of the function. In calculus, the principal technique for this is to differentiate the function that we want to find the minimum for, set the derivative equal to 0, and locate the points that satisfy the resulting equation. This technique can also be used on functions of one or several variables. For example, if we want to find the minimum value of a function f, which has components x1, x2, and x3 in terms of its variables, we look at the points where all three partial derivatives are simultaneously equal to 0. Now, the procedure can be readily adapted as a general-purpose numerical method because it requires differentiation, which we've seen in 407 is rather tricky at points, followed by the solution of one or more equations and one or more variables. This task may be as difficult to carry out using this direct frontal assault on the original problem. So we'll look at some numerical techniques that can help us along the way for finding those function minima. So the minimization problem has two forms. One is unconstrained, where we can look anywhere where the function is defined, and then a constrained version of the problem where we look at a subset K that's in the domain of the domain and range of the function, and we seek a point z is a member of that subset for which f of z is less than or equal to f of x for all x in that particular subset. So in this example, in the R2, or this would be R3, I'm sorry, we have x squared plus x1 squared plus x2 squared minus 2x1 minus 2x2 plus 4. That's a paraboloid, and we would be looking at the unconstrained. If we were able to look anywhere, 1, 1 would be the minimum point of this function. Now, if we constrain this to x is less than or equal to 0 and y is less than or equal to 0, the minimum occurs at 0, 0. So in some ways, the constraint problem is actually more difficult since we need to keep x inside of that subset k, and sometimes k is defined in a more complicated way than what we have in this example. Even in the one variable case, which is what we're looking at, we'll be able to use that to solve a more general case by solving a sequence of one variable problems. So in the one variable case, suppose that f maps r, the real numbers, into the real numbers, and we seek a point z is a member of r with the property such that f of z is less than f of x for all x is a member of the reals. We can have some pretty pathological cases here. We can have a case where there's no minimum. For example, the graph at the top is f of x is equal to 1 divided by 1 plus x squared. There's no minimum there. The curve approaches 0 asymptotically as x goes to positive and to negative infinity, but never quite gets there. So there's actually no minimum. Or, even a function like f of x is equal to x squared plus sine of 53x. That one, you got a lot of local minima, but it may be hard in all those local minima to find the one that's actually the global minimum. We can use mathematical software to find these local minimum values for functions such as f of x is equal to x squared plus sine of 53x. First, we define the function, find the local minimum value in the interval, say minus 1/2 to 1/2, and plot the curve. The point that's computed may not be the global minimum point, but if we wanted to find the global minimum point, we could use a lot of different starting values to find these local minimum values, and then find the minimum of all the minimums. In fact, the local minimum on that interval minus 1/2 to 1/2 is minus 0.99122 at t is equal to minus 0.296, which is in fact the global minimum of this function. So, how lucky can we get? In fact, this time we got pretty lucky. Because of the pathological cases, we'll have to make some assumptions about our function f. And one reasonable assumption is that on some interval a, b given to us in advance, it only has a single minimum. This property is often expressed by saying that f is unimodal on a, b, the interval from a to b containing both a and b. And that's different than the statistical definition for the term unimodal, but here, for our purposes, this is what unimodal means. An important property of these continuous unimodal functions, which might be surmised from these figures, the top ones are unimodal functions, the bottom ones are not unimodal, is that it's strictly decreasing up to the minimum point and strictly increasing thereafter. That's why the middle one on the bottom is not unimodal. It takes a few seconds to look at it, and that after you see it, you see it. Now let's look at some numeric methods that can help us solve the minimization problems. First of these is golden section search, and this method is based on evaluating the objective function at different points in the interval. We choose these points in such a way that approximation of the minimum can be achieved in as few evaluations as possible. The main idea here is what we want to do is we know that minimum somewhere between A0 and B0 here. We want to narrow that range until the minimum point is boxed in with sufficient accuracy. Now, we obviously select the endpoints and then evaluate at two intermediate points. In each step of this iterative algorithm, an interval AB is available from our previous work. This interval is known to contain the minimum point, x star. Our objective is to replace it by a smaller interval that's also known to contain x star. And we keep doing that until we get sufficient accuracy. In each step, we compute two values of f. U is equal to f evaluated at x, and v is equal to f evaluated at y. Now, you'll notice there's an r term here, and here r is equal to 1 over phi, or 1 divided by the golden ratio. And that's why it's called the golden section search. In terms of a decimal approximation, you can use r is equal to 0.61803398875 or thereabouts. Now, there are two cases here. One is u is going to be greater than v, and one is u is going to be less than or equal to v. Let's take the case u is greater than v first. If u is greater than v, we have something like the figure in the upper right. The min of f occurs between a and x, as you can see where the x star is in that minimum point. So this is our next interval. We want between a and x. And we actually have an evaluation of that function at y, which is the v value we got before. Y will play the role of x in the next step, and we find the value of f at r squared x a plus r squared x minus a. And then we make the replacements that you see in the gray shaded figure below the figure. In the case of u is less than v, the minimum lies between y and b, and we have an evaluation point available in that interval at x. X will now take on the role of y, and then we'll be able to compute f at y plus r times b minus y. And again, we make the replacements on the right and proceed with our search. The good news with this procedure is it's quite straightforward compared with others in this section. The bad news is it's a bit slow. And in this context, slowness refers to the large number of function evaluations that we need to achieve reasonable precision. It can be surmised that this slowness is attributable to the extreme generality of this algorithm, which again, generality is a good thing. The slowness, not quite so much. After n steps, the minimum point has been pinned down to an interval of length r to the n minus 1 times b minus a. And again, since r is less than 1, we're going to get better and better as we go on. A very similar idea to golden section search is the Fibonacci search. And this is different than the Fibonacci search that you may have seen before. Here we continually decrease the interval where the minimum is located. That works the same as the golden section search, but the differences are we allow the parameter r to vary at each stage, and we also specify the number of iterations, and the algorithm is limited to that number, so it needs to converge as quickly as possible in that number of iterations. And it's a somewhat more complicated algorithm to code than the golden section search. So basically, the extra complexity of the Fibonacci algorithm, together with the disadvantage of having the algorithm depend on the number of evaluations that we permit, mitigates against its use in general, and the golden section search is probably a better way to proceed. A final technique is the quadratic interpolation algorithm. So suppose that we have our function f represented by a Taylor series in the vicinity of the minimum. Now, we actually have some good news here, because if that is the minimum, then f prime evaluated x star is equal to 0, because it is a minimum. And so f of x can be approximated by f of x star plus 1/2 x minus x star squared f double prime of x star. So, this second equation tells us in the neighborhood of that minimum, f of x is approximated by a quadratic function whose minimum is also at x star. Now, since we don't know x star and we don't want to involve derivatives in our algorithm, a natural strategy is to interpolate f by a quadratic polynomial, which we've seen earlier in the text. Any three values, x sub I, can be used for this purpose. The minimum point of the resulting quadratic function may be a better approximation to x than x1, x2, or x3 if we were using those 3 points. And writing an algorithm that carries out this idea iteratively is not trivial, and there are a few unpleasant cases that we need to deal with. So, what should be done if the quadratic interpolant has a maximum instead of a minimum? We'll take a look at what happens there. There's also the possibility that f double prime of x star is equal to 0, in which case higher order terms of the Taylor series determine the nature of f near x star, which is the minimum. So let's take a look at that algorithm. At the beginning, we have the function whose minimum is sought, 2 starting points x and y, as well as 2 control numbers delta and epsilon. We evaluate u is equal to f of x and v is equal to f of y. We let z equal 2x minus y if u is less than v, and 2y minus x if u is greater than v. In either case, w is equal to f of z needs to be computed. At this stage, we have 3 points, x, y, and z, together with the corresponding function values u, v, and w. In the main iteration step of the algorithm, the polynomial q is determined to interpolate f at the 3 current points of x, y, and z. Next, the point t, where q prime of t is equal to 0, is determined. And under ideal circumstances, t is a minimum point of q and an approximate minimum point of the function f that we're looking for the minimum. So one of x, y, or z should be replaced by t depending upon the nature of q double prime of t. Now, there are 4 cases here. The solution occurs if q double prime of t is greater than 0 and the maximum of t minus x, t minus y, and t minus z is less than epsilon. And basically the condition q double prime of t indicates that q prime is increasing in the vicinity of t, so t is indeed a minimum point of q. Second condition indicates that this estimate t of the minimum point of f is within the distance of the 3 points x, y, and z. In this case, we accept t as a solution. The usual case, again, we have q double prime of t is greater than 0, but the maximum of those differences is greater than epsilon. And that indicates t is a minimum point of q, but not near enough to the 3 initial points to be accepted as a solution. Also, t is not farther than units from each of the x, y, and z, and can thus be accepted as a reasonable new point. The old point that has the greatest function value gets replaced by t, and its function value by f of t. Now, we have a bad case that happens if q double prime of t is greater than 0 and the maximum is greater than that delta. That's the bigger value than the epsilon. Here, t is the minimum point of q, but so remote that there's some danger in using it as a new point. We identify one of the 3 original points that's farthest from t, for example, x, and we also identify the point closest to t, say z. Then we replace x by z plus delta times sine of t minus z, and u by f of x. And the last case is the maximum point. Here we identify the greatest and least amongst u, v, and w, and suppose u is greater than v, which is greater than w, and then replace x by z plus delta sine of z minus x. So there are 4 cases, and we have to deal with those 4 cases for this quadratic interpolation search algorithm. So if you do happen to code that up, those are the 4 that you'll need to deal with. So that's it for minimization of functions. Thanks so much for watching.